Hi, I want to demonstrate today some of the Boolean logic functions in NeatTools. I'm going to open up the display toolbox and I'm going to grab a couple of switches. These stay pushed when you press on them with the mouse, and one LED indicator. Close that. Then I'm going to open up the digital logic toolbox, grab the four basic primitives of Boolean logic. First of all, let me tell you that a Boolean bit is like a switch, that if you push it, it's on or true, and if it's not pushed or switched, it's off or zero or false. All those describe the same behavior. We can see that if we wire up a single switch to the LED. The switch is depressed, so the LED is lit. The switch is off, the LED is off. We can change that behavior and use and add other switches or bits by adding logic gates alone or in combination. Now I'm just going to move and change the behavior of the switch by adding a NOT gate. Now NOT gate's truth table is it's the opposite of whatever comes in. So if off comes in, then on goes out, and vice versa. So if the switch is on, the LED is off. The switch is off, the LED is on. The exact opposite of the behavior we were having before. So the first complex gate, more complex gate I should say, we're going to look at is the AND gate. We're going to wire up two switches, have two inputs, wire up the output to the LED. The LED tells us what the logic state is on the output. So if I depress this switch, LED stays off. If I depress this switch, the LED stays off. Only if both switches are depressed does the LED light up. That's the truth table for an AND gate. We can take the NOT that we had before and create a NOT AND or NAND gate. Unfortunately, right now, NeatTools doesn't have a NAND function. You have to make it up from these two primitives. With a NAND gate, the LED remains on until both switches are depressed. This is the OR gate. Now the OR gate will light up the LED if either or both of the switches are depressed. So that lights up the LED, that lights up the LED, and now both of them being on lights up the LED. We get the opposite behavior by introducing a NOT, wiring it up. The NOT function makes the combined logic, it's called a NOR in the combined logic. Again, you have to make it up from primitives. With the NOR function, the LED is on unless one of the switches or both of the switches is depressed. Only when both switches are unpressed does the LED light. This is the final primitive. This is an exclusive OR. Now exclusive OR is a little different than OR, or the OR function, in that exclusive OR says, okay, I'm only going to light up if one of those two switches is depressed. So if I depress one switch, the LED lights. If I depress the other switch, the LED lights. But now, this is where it differs from the OR. When both switches are depressed, the LED is no longer lit. If both switches are unpressed, of course, the LED remains off. And again, we can have a not exclusive OR. So in the not exclusive OR, we get the opposite behavior of exclusive OR, and the LED lights when both switches are unpressed or depressed, but not if either of the two switches is pressed. As long as both of them aren't pressed, the LED remains off. I've added a third input to this AND gate. These functions do support more than simple binary inputs. And now the AND function says that all three of these switches have to be depressed before the LED lights. If any one of the switches is off, the LED is not lit. With this multiple input AND, this would be true, 4, 5, 6 switches, and all switches would have to be depressed in order for the light to light, or for the LED to illuminate. Here's an example of some more complicated logic. I replaced our switches with push buttons. They change state just for as long as I hold the mouse button. I've got two LEDs. This one indicates Q, or the output, and this is the inverted output, Q naught. So I'm also inverting the pulses from our push button switches. And I'm going to take these and make an input to these AND gates. And now I'm making a NAND gate with a combination of the AND and the NOT. And I'm taking the output of this one and wiring it up to the input of the second NAND, taking the output of the second NAND, wiring it up to the input of the first NAND. This is what's known as a cross-coupled NAND gate. It's a simple set reset latch. So in its default behavior, Q is false, and so isn't lit up, but Q naught is the opposite state, so it is lit. If I push set, Q lights up. Q naught, of course, is unlit. It's the opposite state. And I can hit set as many times as I want, and that output does not change. If I hit reset, we go back to our original state. We've just created a set reset flip-flop. I think it's kind of awesome. Thanks for watching.